morning, everyone. We're the team Transcending Science, and today we'll be presenting our research project titled Atmospheric Water Harvesting. Sustained and Efficient Design for the Future. Our group is made up of Marcelo, Elisa, Emilia, Miguel, and me, Lucia. Water scarcity is one of the most urgent challenges of our century. Millions of people around the world still lack access to clean drinking water, and this problem continues to grow due to climate change and population increases.
In many arid or semi-arid regions, traditional sources like rivers and aquifers are no longer enough. That's why scientists are exploring new ways to collect water, even from places we usually don't think of, like the air itself. One of the most promising solutions is atmospheric water harvesting, also known as AWH.
AWH is the process of extracting water vapor directly from the atmosphere. This can be done through fog nets, condensation systems, or using advanced materials that attract and collect moisture. What makes this technology so interesting is that it can work in areas without rivers, lakes, or rainfall, basically anywhere there's humidity in the air.
Recent innovation in material science and nanotechnology have made AWH more efficient and affordable. For example, some surfaces now mimic the structure of beetle shells or cactus spines to collect water more effectively. And when powered by renewable energy, these systems can operate sustainable in isolated or rural communities.
But innovation alone isn't enough. We must also ask ourselves if atmospheric water harvesting is truly sustainable. Some systems consume a lot of electricity for cooling or air compression, which can increase carbon emissions if they're powered by fossil fuels. Large installations might even affect local humidity or nearby ecosystems if they are not carefully designed.
That's why our research focused on evaluating not only how efficient AWH can be, but also how it impacts the planet. We wanted to find a balance between technological progress and environment responsibility.
Our main objective was to evaluate the environmental benefits and potential negative impacts of atmospheric water harvesting systems on the planet.
And our specific objectives were: 1. To analyze how AWH helps reduce global water scarcity. 2. To identify environmental costs from energy use and material production. 3. To explore renewable energy options such as solar or wind power. And 4. To compare AWH's ecological footprint and with other water supply methods.
This research is important because access to clean water is essential for human health, agriculture, and economic development. If atmospheric water harvesting is designed responsibly, it could be a game changer for communities suffering from drought.
However, without proper analysis, this technology could also create new environmental problems. For example, systems that use non-recyclable plastics or conventional energy sources might help solve water scarcity, but at the same time, worsen pollution or climate change. Understanding these trade-offs is essential to make sure that solutions we create remain sustainable in the long term for this subject.
Our hypothesis states that if atmospheric water harvesting systems are powered by renewable energy and built with recyclable materials, then they can provide sustainable water sources with minimal environment damage.
In other words, we believe it's not just about collecting water, it's about doing it in a way that protects the planet at the same time.
Our research followed a literature-based methodology. We didn't conduct experiments, but instead analyzed scientific papers, documentaries, and technological reports related to AWH systems.
We organized the process into 4 main steps. 1. Reviewing case studies from around the world, such as fog nets in Morocco and solar condensers in India. 2. Identifying the main factors that affect efficiency, including surface area, humidity, temperature, and materials. 3. Comparing different AWH methods like fog collection, condensation, and hydrophilic coatings. 4. Evaluating sustainability through indicators such as energy consumption, cost, and ecological effort.
From the research we compared, we started noticing clear patterns showing that systems powered by renewable energy and built with eco-friendly materials are far more sustainable in the long run.
We expected that our analysis will confirm that renewable powered AWH systems have a lower environment impact than traditional water extraction methods like pumping or desalination.
We also anticipate that the study will identify which materials, such as bio-based polymers or metal organic frameworks, collect water most efficiently under different humidity conditions.
Another expected result is to highlight how combining solar energy with passive condensation techniques can make water harvesting both affordable and sustainable, especially for small rural communities.
In conclusion, atmospheric water harvesting has enormous potential to become a key solution for water scarcity in the 21st century.
By using renewable energy and recyclable materials, we can collect water in a clean, sustainable way.
Atmospheric water harvesting connects different branches of science, physics, chemistry, and ecology, to address one of humanity's biggest needs, access to clean water. If we develop responsibility in this, it can reduce the pressure on natural water sources and become a lifeline for communities affected by drought and desertification.
In short, technology can't just advance from efficiency's sake. It must evolve with the environment in mind. That's the balance our project seeks to promote. Innovation that respects and sustains life on Earth.
Our main references include Brave Blue World, Racing to Solve Our Water Crisis in 2019, the nature study by Park and colleagues on condensation surface, and the research by Sharon and Clues on fog water harvesting from desalination and water treatment. We also consulted Science Direct for recent developments in AWH technology.